Section 1 Introduction. In this introduction, we delve into the world of machine learning, particularly focusing on the importance of choosing the right evaluation metrics to guide model selection and performance understanding. This is especially crucial in critical fields like healthcare. Our study zeroes in on two key metrics for binary classification tasks: the area under the precision recall curve, AUPRC, and the area under the receiver operating characteristic, AUROC. There's a common belief in the machine learning community that AUPRC is a superior metric to AUROC when positive instances are significantly less common than negative ones. This belief is backed by several arguments, some of which we challenge in this study. For instance, it's argued that precision recall curves are more reflective of real-world deployment goals than the receiver operating characteristic, and that AUPRC is not influenced by the large number of true negatives, making it less optimistic than AUROC. It's also suggested that in low-prevalence scenarios, AUPRC is often significantly lower compared to AUROC, and that AUPRC's dependence on prevalence is a beneficial property. However, through careful mathematical, logical, and philosophical reasoning, we demonstrate that these claims and many associated reasons are either invalid or misapplied in common machine learning settings. We show that AUROC and AUPRC are probabilistically interconnected. To illustrate this, let's consider a model that generates scores from distributions for samples with positive, negative, and arbitrary labels. In this case, AUROC and AUPRC only differ with respect to model-dependent parameters in that AUROC weighs all false positives equally, while AUPRC weighs false positives with the inverse of the model's likelihood of outputting a score higher than the given threshold. We refer to this as the firing rate of the model at a given threshold. AUROC favors model improvements in an unbiased manner, while AUPRC prioritizes high-score mistakes first. Let's imagine a static model over a finite dataset. A model makes an atomic mistake with samples if it satisfies three properties over two samples. The first sample is positive and the second is negative. The score of the first sample is less than the second, and there's no sample with a score between the two. An atomic mistake happens when a model assigns adjacent probability scores to a pair of samples with discordant labels. Given a fixed model and dataset, which such mistakes should be prioritized for correction? We propose two possible answers. Don't prioritize any mistake over any other, all improvements are equally valuable, or prioritize fixing the atomic mistakes in descending order of the assigned scores. The first strategy is ideal for classification settings, where a user is given a model and a sample and must decide what action to take based on that sample. The second strategy is only well suited for single-group information retrieval settings, where users use a model only by selecting the top-scored samples with the intent being to maximize the number of positively labeled samples among this subset. We demonstrate that optimization or selection by AUROC corresponds exactly to the first strategy, whereas optimization or selection by AUPRC corresponds to the second strategy. However, AUPRC overtly favors high-prevalence subpopulations. If the underlying dataset can be divided into two separate subpopulations that have markedly different prevalences and our model is reasonably well calibrated, then AUPRC will explicitly favor optimization for the higher prevalence subpopulation first, whereas AUROC will optimize both subpopulations in an unbiased manner. This is a significant concern in domains that frequently feature imbalanced classification problems with diverse patient populations, such as the medical domain. Thus, relying on AUPRC poses challenges to fairness and validity, even in information retrieval settings where fairness among possibly retrieved elements is a concern. Section Summary. In this section, the authors discuss the importance of selecting appropriate evaluation metrics for machine learning models in critical domains like healthcare. They focus on two metrics, AUPRC and AUROC, for binary classification tasks. The authors argue that the widely held belief that AUPRC is a better metric than AUROC is invalid in common machine learning settings. They mathematically show that AUROC and AUPRC are probabilistically interrelated and have different priorities in terms of model improvements. AUPRC prioritizes high-score mistakes first, which can lead to bias towards high-prevalence subpopulations and pose challenges to fairness and validity. Section. The literature regarding this claim is rife with misattributed citations, fallacies, and unchallenged assertions. The existing literature on this topic is filled with inaccuracies, such as wrongly attributed references, logical errors, and unverified claims. We've conducted an extensive review of this literature, both automated and manual, covering 1.5 million and 128 archive papers respectively. Our goal was to understand the prevalence of these inaccuracies and how often they are repeated without proper citation. We found that many references supporting this claim actually don't make the claim at all. Furthermore, the fundamental arguments for this claim are often flawed or misapplied. This study aims to fill this gap in the scientific discussion about metric relationships and selection. Our review suggests two main reasons for the widespread belief that the area under the precision recall curve, AUPRC, is superior to the area under the receiver operating characteristic, AUROC, for model comparison in situations of class imbalance. Firstly, it's often observed that AUPRC values are significantly lower in class imbalance situations, which is interpreted as evidence of AUROC's optimism and AUPRC's superiority. While this observation is correct, it's not particularly relevant when comparing models in a general sense. The key factor in such comparisons is not the absolute metric values, but the relative rankings these evaluation metrics give to the models. The lower AUPRC values can be attributed to its inherently lower chance value in these contexts and the reduced rate of positive samples in models where AUROC is high. However, these facts alone don't support the claim that AUPRC provides a better ranking of candidate models than AUROC. Secondly, it's true that AUPRC can be more indicative of a model's precision or top K retrieval performance compared to AUROC. This difference is mainly due to the way these curves are constructed. However, this doesn't mean that AUPRC is superior in broader contexts of general model comparison. If precision is the main metric of interest, then comparing models based on precision is indeed more appropriate. AUROC has the advantage of providing a more general, unbiased assessment of performance that is not tied to precision. This is particularly important when the primary performance metric is uncertain or when the goal is to optimize performance across diverse subgroups with different prevalences within the dataset. In the rest of this paper, we will formally establish these arguments, using a mix of theoretical reasoning and semi-synthetic empirical analyses. We will delve deeper into the methods and results of our literature search. Finally, we will conclude with some final thoughts. This work aims to challenge existing assumptions about AUPRC and AUROC and encourage a shift towards more robust and evidence-based practices in machine learning. Now, let's discuss the theoretical foundations of our assertions. We will focus on the relationship between AUROC and AUPRC. We will prove a theorem, which is restated below. AUROC and AUPRC are defined as follows. AUROC is the integral from 0 to 1 of the true positive rate, TPR, with respect to the false positive rate, FPR. It can also be expressed as 1 minus the integral from 0 to 1 of the FPR with respect to the TPR. AUPRC is the integral from 0 to 1 of the precision with respect to the TPR. However, we can further clarify these by leveraging the fact that the TPR as a function of a threshold, tau, is equal to the probability that a positive sample score is greater than tau, which can be expressed as the integral from tau to 1 of the distribution of positive sample scores. This allows us to express AUROC as 1 minus the expected value of the FPR for positive samples, and AUPRC as the expected value of the precision for positive samples. Section Summary. The literature on this claim is filled with misattributed citations, fallacies, and unchallenged assertions. Through a review of 1.5 million automated and 128 manual archive papers, we found that many citations for this claim reference papers that don't actually make the claim, and the arguments supporting this claim are often logically unsound or applied out of context. Our study challenges the prevailing belief that AUPRC is superior to AUROC for model comparison in cases of class imbalance, emphasizing that the relevance lies in the relative rankings conferred upon models by these evaluation metrics rather than their absolute values. Additionally, we establish that AUROC offers a more generalizable and unbiased assessment of performance, particularly when the primary performance metric is indeterminate or when optimizing performance across diverse subgroups with different prevalences within the dataset. The rest of the paper will present formal arguments, discuss the methods and results of the literature search, and conclude with thoughts on elevating the discourse in machine learning. Section 2.2 Relative prioritization of atomic mistakes. In this section, we delve into the relative importance of different types of errors in a model, as determined by the evaluation metric used. This understanding is crucial as it sheds light on the characteristics that the metric will encourage when used for model optimization or selection. We specifically focus on how AUROC, area under the receiver operating characteristic, and AUPRC, area under the precision recall curve, rank the importance of correcting individual errors in a model. Let's start with a theorem. We previously defined an atomic mistake as a single error in the model. The theorem states that the improvement in a model's AUROC is the same, regardless of which specific error is corrected. On the other hand, the improvement in AUPRC is directly related to the score that the model assigns to the samples in the error being corrected. To prove this, let's imagine a model with a certain set of atomic mistakes. We then create a new model by correcting one of these mistakes. We do this by swapping the scores assigned by the original model to two samples involved in the mistake. Now, we ask ourselves, under what conditions will the number of false positives in the new model differ from the original model? The answer is that it depends on the threshold we choose. If the threshold is less than the score of the lower of the two swapped samples, or greater than the score of the higher sample, correcting the mistake won't change the number of false positives. The only threshold that will make a difference is the one equal to the score of the lower sample. In this case, correcting the mistake will reduce the number of false positives by 1. This shows that AUROC will improve by a fixed amount, no matter which atomic mistake is corrected. This is because AUROC gives equal weight to the false positive rate at all positive samples, and the false positive rate is proportional to the number of false positives. In contrast, AUPRC gives more weight to false positives at higher scores and less weight to those at lower scores. This means that AUPRC will improve more when mistakes involving higher scores are corrected. This theorem reveals that optimizing or selecting a model based on AUPRC will favor a model's ability to discriminate in regions where the output score is high, while AUROC is unbiased in where it values model improvements. This clarifies the claim that AUPRC should be preferred in cases of class imbalance, and raises serious concerns about the general use of AUPRC. Moving on, we argue that AUPRC is more suitable for single group retrieval tasks, not for binary classification tasks with class imbalance. This contradicts the common belief that AUPRC's preference is due to class imbalance. Instead, the choice between AUPRC and AUROC depends on whether the metric should be optimized in a biased or unbiased way. In information retrieval tasks, where a model only selects the top K items for evaluation, it makes sense to prioritize corrections in high-score regions. This ensures that the metric focuses on the most relevant part of the model's output for the task at hand. However, in other applications, such as diagnostic predictions in healthcare, the focus is on individual predictions rather than a ranked list. For example, a doctor using a model for patient diagnosis cares about the model's accuracy for the specific patient being examined, not for the top K patients in the overall dataset. Therefore, in such settings, especially when dealing with rare conditions, optimizing or selecting models based on AUPRC would be inappropriate. Section Summary. The authors prove that the improvement in a model's AUROC, area under the receiver operating characteristic curve, is independent of the specific mistake corrected, while the improvement in AUPRC, area under the precision recall curve, is positively correlated with the model score assigned to the samples in the mistake being fixed. This implies that AUROC is unbiased in valuing model improvements, while AUPRC favors mistakes with higher scores and disfavors mistakes with lower scores. Therefore, the decision to use AUPRC or AUROC depends on whether the metric should be optimized in a biased or unbiased manner, with AUPRC being more suitable for single-group retrieval tasks and AUROC being more appropriate for class-imbalanced binary classification problems. Section 2.4 AUPRC is explicitly discriminatory. We're going to discuss a potential issue with the area under the precision recall curve, AUPRC, a metric often used in information retrieval. The problem is that AUPRC can be biased, favoring groups with higher prevalence rates. This is because AUPRC depends on the rate at which a model fires or activates. In datasets with different subgroups, each having different prevalence rates, a well-calibrated model might favor the high-scoring regions. This means that AUPRC could unintentionally favor groups with higher prevalence rates, putting those with lower rates at a disadvantage. This is a significant concern in fields like healthcare, where it's crucial to have fair model performance across diverse patient groups with different disease rates. Our experiments show that AUPRC tends to prioritize improvements in groups with higher prevalence rates. This is a serious risk and suggests that AUPRC might not be the best choice for an evaluation metric. This isn't just a theoretical risk. Our experiments show that optimizations driven by AUPRC tend to favor high prevalence groups. This highlights the need to reconsider using AUPRC as an evaluation metric, given its potential to perpetuate disparities, especially in critical fields like healthcare. To support our claims about the area under the receiver operating characteristic, AUROC, and AUPRC, we conducted several experiments. We tested each theorem and proof one by one. All of our experiments can be replicated and validated. To validate our theorems, we created synthetic scores for positive and negative labeled samples for models across a range of possible AUROC values and prevalence values. We confirmed that the relationships we predicted in our theorems hold true with high numerical precision in all settings. The details of these comparisons are quite technical, so we've included further details in the appendix. More importantly, we wanted to validate our findings that AUPRC can be a discriminatory metric. To do this, we created a synthetic dataset of model scores and labels for a population containing two distinct subgroups with different prevalence rates. We then optimized the initial scores over several iterations. We assumed that the model developer doesn't know the subgroup labels, so the optimized score can only be selected by either overall AUROC or overall AUPRC. We tracked how the overall and per subgroup AUROC and AUPRC metrics changed throughout this process. In our experimental setup, we had two subpopulations. We set the prevalence rates for the first group at 5% and for the second group at 1%. We created a dataset for each group, ensuring that the AUROC for each group and the combined group was approximately 0.85. Our main challenge was figuring out how to simulate the process of optimizing or selecting a model by AUROC or AUPRC. We tried two approaches. First, we corrected the single biggest mistake that would most improve AUROC or AUPRC in each optimization iteration. This is the simplest possible optimization procedure to analyze, but it's not very realistic. In real optimization scenarios, larger model changes will be made at once, and a model will have an opportunity to degrade performance in some regions in order to improve it in others. Simulating a more realistic optimization process is challenging. One idea might be to simply perturb the assigned model scores by a random noise vector of fixed magnitude a fixed number of times, and output the perturbed model scores that optimize the target metric. However, this approach is subtly biased in favor of the lower prevalence group. To account for this bias while still providing a more realistic optimization procedure, we also profiled an optimization procedure that randomly permutes all the sorted model scores up to 3 positions. This has the effect of randomly adjusting all model scores, and can worsen model performance under some random permutations, but offset precisely the same capacity to the low and high prevalence subgroups. To ensure the model is under some optimization constraint, and therefore does not always find the perfect permutation to maximize both metrics identically, we allow the model to sample only 15 possible permutations before choosing the best option. This means the system will be forced to navigate optimization trade-offs between which permutations improve the right regions of the score most effectively among its limited set. Across both settings, we ran these experiments across 20 randomly sampled datasets and show the mean and an empirical 90% confidence interval around the mean in figure. We present a formal mathematical formulation of these perturbations, as well as profile some aspects of the random perturbation method of optimization, despite the possible biases it has, in the appendix. Section Summary. The AUPRC evaluation metric, despite its potential relevance in information retrieval settings, introduces fairness concerns due to its reliance on a model's firing rate. In datasets with varying subpopulations and prevalence rates, AUPRC may unintentionally favor higher prevalence subpopulations, disadvantaging those with lower prevalence. This issue is particularly problematic in sectors like healthcare, where equitable model performance across diverse patient groups is crucial. Synthetic experiments demonstrate that optimizations driven by AUPRC significantly prefer high prevalence groups, highlighting the need to re-evaluate the use of AUPRC as an evaluation metric to avoid perpetuating disparities in critical applications like healthcare. Section: Results. Our research highlights the influence of the optimization metric on the disparity among subpopulations. Specifically, we noticed a significant disparity when optimizing under the AUPRC metric, as shown in our figures. This disparity is most noticeable when comparing the performance metrics of subpopulations with high and low prevalence. The optimization process tends to favor the group with higher prevalence, which can even lead to a decrease in the AUROC for the second group in a more realistic, random permutation optimization procedure. However, when we optimize for overall AUROC, the AUROC and AUPRC of both groups increase together. A common belief in the field is that AUPRC is better than AUROC in cases of class imbalance. This claim is widespread in the literature, and we found 128 publications asserting this through both manual and automated searches of over 1.5 million archive papers. We delved into these papers to understand why this incorrect claim is so prevalent in machine learning and to extract any correct insights from the ongoing scientific discussion. Interestingly, this claim is often stated without any citation. Out of the 128 papers we found referencing this claim, 31 did so without any associated citation. These papers were published in various venues, from Archive to Nature Scientific Reports, ICCV, ECCV, and Bioinformatics, among others. This reflects not only the widespread belief in this claim but also the comfort in making seemingly correct assertions without proper attribution in the machine learning field today. Moreover, this claim is often attributed to papers that do not make this claim. Among the 97 papers that reference this claim and cite a source, 39 do not cite any papers that actually make this claim. This reflects poorly on the accuracy of our scientific discourse in machine learning today. The ROC curve represents the trade-off between the true positive rate, TPR, and false positive rate, FPR, at various thresholds, while the PR curve focuses on the trade-off between precision and recall. AUROC and AUPRC are the respective areas under each curve, providing an overall reflection of the model across all thresholds. While PR curves can be more informative than ROC curves as they may more appropriately reflect deployment objectives, the utility of the curve itself is distinct from the utility of the area under it. The claim that AUPRC is universally superior in all cases of class imbalance often overlooks the nuanced differences between the curves and their corresponding area metrics. Unfortunately, papers that do make variations on this claim are often misunderstood, miscited, or outright wrong. For example, some papers argue that, because AUPRC is often lower for datasets with low prevalence, it has greater discriminatory power between poor and good models in this setting. This argument is not sound. The utility of a metric for model comparison is driven by how it separates models. From our mistake correction framework, it is clear that what differentiates AUROC and AUPRC is that AUPRC favors improvements in regions of low firing rate, whereas AUROC is unbiased. This can be valuable in single-stream retrieval settings, but is far from indicative of general superiority in cases of class imbalance, and is dangerous from a fairness perspective. Section Summary. The results of the study show that optimizing under the AUPRC metric introduces significant disparities in performance across subpopulations with different prevalences. This contradicts the widespread claim that AUPRC is better than AUROC in cases of class imbalance. The claim is often made without citation, misattributed to papers that don't actually make the claim, and based on unfounded arguments. Section. Prior mathematical analyses have found complementary perspectives to our findings regarding the nature of the AUPRC. We've discovered some interesting mathematical insights that align well with previous research on the nature of the area under the precision recall curve, AUPRC. These findings, while new, resonate with earlier studies. For instance, it's been demonstrated that both the area under the receiver operating characteristic curve, AUROC, and AUPRC can be interpreted as weighted combinations of the same elements. The difference lies in the weights. AUROC uses weights that are independent of the model, while AUPRC uses weights that depend on the task or model. This distinction is fully exposed in our analysis. However, some researchers argue that this characteristic of AUPRC is advantageous, despite the clear implications it has for its usefulness and potential fairness. Additionally, it's been shown that when both AUROC and AUPRC are adjusted to fall within the range of 0 to 1, the AUPRC is roughly equivalent to the AUROC multiplied by the model's initial precision rate. This is used to justify the use of AUPRC for retrieval tasks. Our framework, however, provides a clearer picture. It shows that AUPRC consistently favors enhancements to models starting from the highest scoring region, providing a more comprehensive justification for this preference. There are also other factors that might lead one to favor AUROC over AUPRC. For example, the fact that AUPRC is dependent on prevalence can make it difficult to use as a metric for identifying disparities among subgroups, as different subgroups may have varying prevalence rates.